Any sufficiently advanced technology is indistinguishable from magic.
Hello, I'm Professor Brian Keating, the co-director of the Arthur C. Clarke Center for Human Imagination at the University of California, San Diego, and I'm also the Chancellor's Distinguished Professor of Physics as well. Today we're going to be talking about the limits of imagination with inspiration from our namesake, the person who gave us the name of this podcast, Into the Impossible, Arthur C. Clarke, who said the only way of discovering the limits of the possible is to venture a little way past them into the impossible. And of course, imagination goes hand in hand with science and curiosity. And my motto, of course, is always be curious, ABC. Because that will stoke the imaginative fires that we need to proceed and make progress in physics. And no one was more of a big supporter of that than Albert Einstein, who said famously, imagination is more important than knowledge. I don't know, sometimes I like to have my surgeon have good knowledge too. I don't want them to be too imaginative when they're doing stuff down there, but nevertheless, I hope today you're going to be inspired by a little discussion that I've been working on along with my late great colleague Andrew Friedman, and that's called How Big is the World? How big is the universe? And are there other universes? This is a question as old as time. So from ancient days, people used to draw pictures of the universe as they knew it, the world, and ask questions. How big is it? And there they would say, there can sometimes be dragons here. And we can look back in this early illustration over here. That's the Flammarion woodcut that shows a figure peering out into the distance and seeing what lies beyond, what you can see, the limits of your own mind. And you can see things in your mind that you can't see with your eyes, as this individual is depicted doing. Now, what I'm curious about is what are the improvements that we've made in our understanding of the universe? So the first kind of revolution I talked about in my book, Losing the Nobel Prize, and the so-called 5 great debates, centered upon whether or not our position in the universe is somehow privileged or not. And Copernicus and Galileo and others helped to answer this question that the Earth is not the center of the universe. But today, the question of the multiverse, one can ask legitimately, is ours the only universe? Or are we a population set contained within the multiverse? And are we the center of the multiverse? Where do these notions of the multiverse come from? So we don't believe we're the center of the universe, and yet we know that there are horizons. And so it turns out there's a limit to what we can see. Here in San Diego, we can go out to the ocean, we can look upon it, we can see boats coming from over the horizon. So we know there are things out there. We can even learn about distant processes, earthquakes, tsunamis, and things that travel from far distant locations before they reach us. We get their signals not in the form of light that we could see, but in the form of other forms of information. Now, it turns out many scientists have looked into this question. How many different types of multiverse are there? And it turns out there's more than just one, there's more than 2, and perhaps there may be as many as 4. So the question of how many different types of multiverses there are is a rich question, and it dovetails in with the Copernican Principle rather nicely. Because the question is, how can we test for the existence of multiverses, and what evidence do we have for other types of properties that we can access using just our current set of observations? So we have evidence for other planets, other stars, things beyond the horizon, and so forth. Those have been replete for many years. So the next question is, are there other universes? This is what I call the next or 5th great debate. We know we can access other places by land, and this has been known since the cave dwellers thousands of years ago, depicting people walking. And you can go out and access other places by land quite easily. You can also take a boat and go over other places by sea. People have known about this for so long. So these are ways that we access other regions that you can't see from a current location by physically transporting yourself. You can also observe things that you can't physically transport yourself to, other planets. Here are depictions over the centuries of planets like that of depicted by Galileo, who's shown with a telescope much bigger than the actual one he used. But nevertheless, it gives you an idea, peering out in the early 1600s and seeing things like the moons of Jupiter and the lobes, or ears as he called them, of Saturn. So these are all things we can encounter without going to them, so you can see them. We can see other stars. We've never been to another star. We can see other galaxies, even with your eye. You can see the most distant thing you can see with your eye is the Andromeda galaxy, about 3 million light years away. That means the light left that galaxy when there were still hominids in Africa roaming around the Serengeti Plain, millions of years ago, predating Homo sapiens. We see the Hubble Deep Field, the Hubble Ultra Deep Field, and we see that almost every image, every speck of light in this image is a galaxy, not a star, in our Milky Way galaxy, but another galaxy itself. A galaxy cluster, many galaxy clusters in the Hubble Deep Field and beyond. And if you just simply make a calculation, an estimate from this image or the Hubble Deep Field image, you can estimate how many galaxies are there approximately in the visible universe, and it turns out to be about 100 billion galaxies that we could observe just in our observable universe since the creation of our observable universe 13.8 billion years ago. So it's natural to want to think about, well, there could be other universes. Here's a picture of the cosmic microwave background as we see it, depicted as sort of a deity looking out at our universe. I also happen to have a model of our universe in this form. It's a beach ball. This one differs from that one because it has the galaxy, which is replete with emission from dust, from electrons zipping around. And the actual universe that we observe with microwave vision is quite indicative of a process that took place very long ago that cast the die in terms of the patterns that we now see. So some of the earliest multiverse ideas are really tied to the ancient idea of kind of the Copernican Principle, which is one of humility, that we are not the center of the solar system, the galaxy, the universe, and perhaps maybe there's even more to our universe. These sometimes go by the name of bubble universes or isolated universes, and theories that we'll discuss on this channel as well. Well, we can look back in cosmic history as depicted here, a modified plot courtesy of NASA, and it shows the universe starting from a period of early inflation, which is our best candidate model for how the universe may have emerged from some initial condition. It is not a theory itself of the initial conditions, but it's a theory of perhaps best thought of as a way to get structure forming models to work in the early universe, but by no means is it the only theory. There are other theories that we will explore on this channel, including bouncing and cyclic cosmological models. The universe evolves, it creates hydrogen. Hydrogen at 380,000 years after the Big Bang produced the CMB at that same epoch. We then observe the CMB, and we're hoping to use patterns in the CMB to infer what the universe might have been like at times predecessing to when we observed the cosmic background radiation. So we have evidence. We have evidence for these cosmic processes. We have evidence for matter. We have evidence for a very, very brief but energetic phase of the universe called Big Bang nucleosynthesis, when the elements like hydrogen, helium, and their isotopes formed the lightest elements in the periodic table. And we also have evidence in the form of matter and light that we see from the cosmic microwave background and from even our local Earth environment. We can actually get a handle on what the early universe's properties must have been like. And it was an early fusion reactor, which only can take place at extremely high temperatures and extremely high densities. Now, how did it get into that state is the subject of inflation and other models that we'll discuss in other videos. So the question of how far you can see is a question of horizon. One of horizon, just like on the ocean, if you're at sea level, you can only see a certain distance until your eye is not possible to glimpse things beyond it because the Earth curves away. And so what is the farthest distance we can see in the universe back to the so-called Big Bang event, when the universe synthesized the lightest elements in the periodic table? And it's important not to conflate the origin of the universe with the Big Bang. It may be that the Big Bang was the origin of time, but it may not be. And there are other models that we'll talk about, including videos with Julian Barbour and others that have different theories of time, different theories of singularity-free origins of the universe. I hope to get into all of that in future episodes. We can actually do calculations. This is a calculation from my course in cosmology with Professor Barbara Ryden's wonderful book, and she is a guest on the Into the Impossible podcast. We'll have a link to that video as well. And this is in her chapter 5, just to show you what some of these equations look like. But actually, we can calculate them quite accurately thanks to the observational input data that define the matter and energy content of our universe as we observe it today. Then using the known laws of physics and assuming the constants of nature do not change over the course of the universe, we can propagate those back in time. And we can ask, what was the universe like at previous eras in our history? And what will the universe be like in the future? We can make hypotheses as to what will happen. And in so doing, we come upon an inescapable fact, at least in the context of inflation, that there may be what's called a multiverse. But the first kind of notion of the multiverse is that there could be a universe outside our universe within our universe. Namely, we can only see back to the creation of the Big Bang, the elements that produced signals that we can see. And that occurred 13.8 billion years ago, but because the universe has expanded since then, the actual radius or if you like, the diameter of the observable universe is more like 92 billion light years. More than 3 times in radius what you'd expect naively from just multiplying the speed of light times the age of the universe. And there could be actually stuff outside of that. People ask me, what's beyond that? Well, I like to say, if you go out outside the space station with a little box and you fill up that box, it'll have some stuff in it. It'll have photons in it from the sun, some photons from the Big Bang in the form of the CMB, maybe a proton or two, some dark matter sprinkled in, some dark energy. We don't know much about that. But it will have all these things inside of it, and then between those things there'll be nothing. So it could be that's what we're expanding into. There could be some vast, enormous space, every point possible, an infinite number of points that are possible in space and time, extending in all directions, north, south, east, west, backwards, and forwards, in all directions, and we can only see back to where a creation event occurred such with long enough time in the past that we are just now receiving information from what's called the surface of less scattering, this teal-colored circle depicted here. So, but that's not everything, or it may not be everything. It could be everything. There may be nothing outside of the entire universe or the cosmos or the megaverse or whatever you want to call it without there having to be multiple universes like ours. Could be that there are other things out there. Could be there's nothing out there, nothing being exactly what's outside the space station. So there could be other universes that would have their own kind of CMB beach balls. That could have the same laws of nature that we have, the same physical Newton's laws, Einstein's laws, Schrodinger's laws, et cetera, et cetera. And it could have the same constants of nature, the same gravitational force constant, the same speed of light, but it would have different initial conditions, and therefore the exact pattern that we see would look slightly different. The same way that breeding a chicken or something like that, you can start with roughly the same ingredients, but you can get a different organism from that. Now, we don't know where the initial DNA comes from, where the structure comes from. It doesn't come from evolution itself. There's an origin of life problem. We'll talk about that as well as many other fascinating aspects of life on this channel in subsequent videos. So we know that there are possibility for the universe to be occupying some space of a greater, possibly infinite set of space that doesn't violate our known laws of the universe. So inflation plays a big role in the multiverse theory, and including its 2 major proponents, Andre Linde, Alan Guth, that worked the hardest on inflationary cosmology in the last 30 to 40 years. They basically say you cannot escape the multiverse if you have inflation. And because the universe appears to be consistent with inflation, so the story goes, there must have been something like inflation that took place. Therefore, there must be something like a multiverse. It's unavoidable. What does inflation do? Well, it solves several cosmological problems that were once thought to be impossible to not solve and still call yourself possessing of a proper theory of cosmogenesis or the origin of the universe. It makes many, many testable predictions, and it also can predict that there are regions of the universe that could be much larger, much vaster than we could ever hope to see with the telescope that we have operating today. There's also possibilities, intriguingly, that come from the science of black holes. We've done lots of videos on black holes, including this one that I'll put with Dr. Delilah Gates, Black Hole Basics, and also her PhD thesis lecture. We'll have that up as well. So what's inside a black hole? Well, nobody really knows. Nobody's been there. Could there be wormholes that connect Einstein-Rosen bridges, as they were once known, where you could teleport effectively from one branch of the universe to another one, seemingly faster than the speed of light, because you basically excise the distance between 2 nominally very far separated points. So we don't know what's in there. This is a diagram that my late great colleague Dr. Andrew Friedman made in connection with Lee Smolin, and has popularized some of these ideas of cosmic Darwinism, that the more black holes that are produced in the universe, universes, kind of their fecundity depends on the number of black holes and the type of black holes they produce. So Andy made these wonderful diagrams of what could happen inside of a black hole, just again, this is a tribute to him as much as to any of the other types of scientists that we'll be talking about today. Now, eternal inflation is a concept popularized in large part by Andre Linde up at Stanford University, who has said things to the extent that we shouldn't be biased towards a prejudice that there's only one universe. In other words, in his conception, there could be multiple universes more naturally than single universes. And in such universes, in the multiverse, it's hard, he claims, for inflation to happen only once. In other words, there's inflation going on all the time in all locations in this superspace of events, in what's called eternal inflation. There's also something called the string theory landscape, which predicts that if string theory is true, there are actually multiple dimensions beyond the 3 spatial dimensions and 1 time dimension. And actually those space-time dimensions can effectively be thought about as inaccessible dimensions that we don't have access to. And actually the number of so-called vacua of compact manifolds and their properties are so numerous that actually each one could be identified isomorphic to another universe, a universe with different physical constants, different physical laws, in what's called the string theory landscape. That leads to many possible universes. And in eternal inflation, you basically seed or spread out the possibility for eternal inflation to populate the string landscape. Now, level 2 multiverse is where you have different post-inflationary bubbles. So in other words, the laws of physics, the laws of mathematics can be the same, can be considered the same, but the laws of nature, the constants that we observe, gravitational constant, speed of light, etc., would be different in such universes. Now, is there any evidence for them? Well, if we didn't have a CMB and we didn't have some properties consistent with inflation, we could rule this type of behavior out. So the fact that we have these two observations, consistency with some aspects of inflation, although some like Paul Steinhardt and others have objected to that as a criteria for scientific progress, nevertheless, we could also hope to explain why our universe is so finely tuned. At least our part of the universe is just a lucky Goldilocks universe that happened to inhabit a region of this vast string landscape populated by eternal inflationary cosmic bubbles, and that was bound to have just the right constants of nature, as I explained in a video called The Faith of a Physicist. Look for that video as well. So now, do we have evidence for fine-tuning? Well, we are sort of here, and so that gives powerful evidence that life evolved at least in one corner of the universe, so the conditions must be comprehensively commensurate with the existence of intelligent beings who can ask questions about the origin of life and, in fact, ask why they're here, and that's kind of associated with the weak Anthropic principle. With many universes, you can turn the dial an infinite number of times, perhaps. So one of them is bound to be right, and then we find ourselves in a universe where these constants are finely tuned for life. We've had conversations about that with Stephen C. Meyer, who rejects that hypothesis and looks for another underlying interpretation. Now, we see this in the universe, at least in our local corner of the universe, our galaxy. Our solar system is populated by objects in the so-called habitable zone around a temperature, a star temperature about 5,500 Kelvin, produces a habitable zone where water can be liquefied. And we do believe that liquid water is some kind of a prerequisite, maybe some other solvent, liquid phosphine, I don't know, could be considered a prerequisite for life. So at least the physical constants of our universe are compatible with life and conscious life at that. But if you had many universes, they could all have different constants. And that would be like saying, well, we find ourselves at the exact distance we do, not because there was some tuner, but because the laws of gravity, and there's so many different objects that could have formed planets. Eventually, the logic goes that one was bound to be at just the right distance to support liquid water. And in fact, the Earth is the dominant source of liquid water in our solar system, but there's many other forms of water in our solar system alone, let alone in other solar systems. So there is a problem that came to pass, which is called the cosmological constant problem, that we seem to witness that the universe is accelerating. It's getting farther and farther apart at a faster and faster rate. Galaxies are moving farther and farther away from each other. We've known that for 100 years almost. But those galaxies and the rate at which they're moving is also increasing with time. For this, the physicists pictured here, Schmidt, Rees, and Perlmutter, were awarded the 2011 Nobel Prize. And now, if you compare what you observe, what these gentlemen and others have observed since, it differs from the predicted value by 120 orders of magnitude. And this is quite embarrassing. Although some people like Steven Weinberg have made claims that if lambda were too big, the universe would expand too fast to form galaxies. In other words, it would be rapidly expanding apart, and effectively it would expand forever, and we'd never get the nucleating force that's required to produce galaxies. Galaxies are required to host stars, stars host people, people are what we are. So if the multiverse exists, there is a hope for this anthropic explanation that some of these universes do exist where lambda is too big, never forms. Or some are too small. We don't know if that would cause a problem to create life. Then there's what's called the level 3 multiverse. We talked about this with Sean Carroll, where effectively at any moment a quantum measurement or quantum process could take place, the universe splits into parallel branches. And in different branches of the so-called universal wave function, the universe behaves differently. This universal wave function, this is obviously quite controversial. This is an interpretation of quantum mechanics that explains the measurement problem and actually has some input into so-called quantum computers. I wouldn't count this as evidence per se, direct evidence that the many worlds interpretation is true. But if we didn't have the double slit, of course, we wouldn't be here to ask such questions, because we seem to believe that the fundamental theory of quantum mechanics has this particle-wave duality and has this measurement incompatibility problem. That's be the subject of another video some other time. But we don't know for sure that there's any evidence per se that it's definitely true. The last level of the multiverse is called the level 4 multiverse, and this exists sort of in the mind of mathematicians. This is really popularized by Max Tegmark and others. And this is that every mathematical object could exist, but that also means that other universes would have different laws of not only physics, but of mathematics. Mathematical structures. We have groups and sets and fields and rings. There could be some other object we can't even conceive of. We don't know why math works, as Wigner said, so effectively for mathematics in physics. Again, this is just a question right now of philosophy. The multiverse isn't so much a theory as it is a paradigm. It has some explanatory power to explain things like the Anthropic Principle, but it is, at best, a consequence of inflation, which itself, at least in the context that I study at the level 1 and 2 multiverse, but it is not yet at the level of a theory. So we don't actually have to test all possible predictions, but we have to find some, and the question is, can inflation be falsified? And that's a big problem for many people, according to folks like Anna Aegis, Neil Turok, and Paul Steinhardt. Of course, there could have been things that you could have falsified about inflation already, namely the flatness of the universe is not falsified, and you can't really, if it were to be falsified and there was a slight positive or negative curvature, that would have falsified that. So we can't right now see the entirety of this megaverse, this ultimate universe. We can talk about the different levels of physical theories that we know about. We can attempt to probe quantum theory better to understand the many worlds interpretation multiverse scenario and understand how that could or could not be tested. According to Sean Carroll, it can be tested experimentally, although to my mind and to my knowledge, it has not yet passed a test that could be falsified, therefore motivating it. So right now it is a matter of almost philosophy of science in terms of, does the many worlds explain more powerfully than, say, the Copernican interpretation? The last multiverse level, level 4, is the universe mathematical? Is the multiverse mathematical? That is a very, very tantalizing and interesting concept to think about. So I'll leave you with these references. We're going to go into each one of these topics in more and more detail. For now, I want to recommend to check out some of the videos I mentioned, and also check out some of these books that are mentioned up here.
If you enjoyed this video, you definitely want to check out this playlist with my cosmology friends talking about the origin and evolution of the universe. And if you're interested in a deep dive in the multiverse, wormholes, and other exotic phenomena, click here and hear my conversation with Juan Maldacena of the Institute for Advanced Study. Enjoy, and don't forget to subscribe for more amazing content.